All right, welcome everybody. So in this video, we are going to work with changing between two bases for a matrix vector space, and we'll set up a change of basis matrix to do so. So in this example, our vector space V is going to be symmetric 2 by 2 matrices. And so when we say symmetric matrix, that means that the off-diagonal entry in position 1, 2 should equal the same as the off-diagonal entry in position 2, 1. So that would be symmetry, and when we talk about symmetry, that means reflecting over the diagonal. So for 2 by 2 symmetric matrices, we actually have a basis B, which consists of 3 elements. So this is a 3-dimensional vector space. One element in a basis could be the matrix that has first column 1, 0 and second column 0, 0. And that's going to allow us to put any value we want in the 1, 1 position. To get the off-diagonal entries, they need to be equal to each other. So we can represent a basis element here, which is a 2 by 2 matrix whose first column is 0, 1 and second column is 1, 0. And that's going to give us whatever we put over here in the 2, 1 position. That means the 1, 2 position is going to have the same value. And then our last basis element is the matrix, 2 by 2 matrix, whose first column is 0, 0, and second column is 0, 1. And that's going to allow us to get whatever value we want in this second diagonal position. So this might be what we consider sort of a standard basis for this space. This is a pretty nice looking basis. Over here, we have some other set of 3 matrices of very kind of weird looking matrices. But notice all of these matrices are at least symmetric. So these are, in fact, objects that live in our vector space of 2 by 2 symmetric matrices. So for basis C, we have the first basis element is the matrix that has first column 1, minus 2, and second column minus 2, 2. And then the second element in this basis is the matrix whose first column is 0, 2, and second column is 2, 4. And then the third element in this set is the 2 by 2 matrix whose first column is 3, minus 1, and second column is minus 1, 1. So here we have a set of 3 elements, and we'd like to show that C is actually a basis for V. We actually don't know this off the top of our head. So to prove that C is a basis for V, what we can use is the result that C is a set that contains the same number of elements as what we know basis B contains. So if I can show that these 3 elements, these 3 matrices in set C are linearly independent, then by previous theorem, we know that they are going to have to span the set and thus be a basis. So I just need to show that these 3 matrices are linearly independent. There's no way that I could take linear combinations of 2 of them and get a third one. And so one way to show that C is a basis, therefore, would be, let's consider the change of basis matrix to go from basis C into basis B. So I know that these vectors are linearly independent in basis B. And so we can construct this matrix by taking each of the elements in our set C and expressing them in B coordinates. And so taking C1 and writing it with respect to B coordinates, that can give me the first column of my change of basis matrix. The second column I get expressing C2 in B coordinates, and the third column we get by expressing C3 in B coordinates. And expressing each of these matrices relative to their B coordinates, if we can show that in B coordinate world, these 3 elements are linearly independent, then that means they must be linearly independent, and that means that C is going to be a basis. So we can take C1, C2, and C3 and write them in terms of their B coordinates by saying the first entry would be what's the first diagonal entry. Then basis B, element B2 gives us the off-diagonal entries. So that's where the minus 2 comes from. And then the third entry, when we represent this with B coordinates, would correspond to the other diagonal entry, which in this case is 2. So we have a 2 over here. For C2, when we write this in B coordinates, we have 0, 2, 4. C3, when we write in B coordinates, this would give us 3, minus 1, 1. And that's where the 3, minus 1, 1 comes from when we take C3, write it in B coordinates. And now that we have these three vectors, namely C1, C2, and C3 written with respect to B coordinates, we can now set up the change of basis matrix from basis C into basis B. And that basis, that matrix is going to have first column 1, minus 2, 2. That comes from writing C1 in terms of B coordinates, and then 0, 2, 4. And finally, the third column is 3, minus 1, 1. And then what you can do is calculate the determinant, look at the pivots in this matrix, use any sort of result from the invertible matrix theorem. But if you prove that this matrix is indeed invertible, then we know that the columns are linearly independent, and that would mean that these three matrices in set C are linearly independent. And so since we have a set of three elements that are linearly independent, and our vector space V is dimension 3, that tells us that this basis, or this set C, is actually a basis for vector space V. And now that we have this change of basis matrix, for example, if I'm given some coordinates for a matrix with respect to the C basis, so for example, I have some matrix which is 2 times C1 plus 1 times C2 minus 5 times C3, we can convert this straight into coordinates relative to basis B by applying this change of basis matrix. So I'm going to multiply P sub C into B, this change of basis matrix. I'm going to multiply the vector in C coordinates by this matrix. You do the arithmetic, and we wind up with vector minus 13, 3, 3, which is being written, it's expressing this symmetric matrix relative to basis B. And so then we can go ahead and convert this back to what it would look like as a matrix. So this first position with respect to basis B is telling us which entry is right here. So that's why we have a minus 13 over here. This second entry is telling us what the off-diagonal entries are. So these are 3. And then this third entry is telling us what the second diagonal entry is, and that is also 3. So this matrix in C coordinates, which we haven't even written out what this matrix is, we can express it relative to B coordinates. And once we have it in B coordinates, it's a little bit easier for us to then express what that looks like as a matrix.